In 2.19, we start with a Fourier theorem function, f of x equals an infinite sum of sine and cosines, and we're asked to convert this into a complex exponential form and also relate the coefficients an and bn to cn. So immediately, since we're converting between sines and cosines to exponentials, we can use sort of Euler's identity to do that. So sine of x is equal to e to the ix minus e to the negative ix all over 2I. And we also have cosine of x is equal to e to the ix plus e to the negative ix all over 2. We plug these in, and what we get is f of x is going to equal some infinite summation from n equals 0 to infinity of an times e to the ix minus e to the negative ix all over 2I plus bn e to the ix plus e to the negative ix all over 2. And then from here we expand this out, n equals 0 to infinity, and then let's see, what does this give us? an over 2I times e to the ix minus an over 2I times e to the negative ix plus bn over 2 times e to the ix plus e to the negative, plus bn over 2 times e to the negative ix. And if we want to sort of write this in terms of the sine and cosine arguments, which is n pi x over a, then this is going to give us a summation from n equals 0 to infinity of an over 2I times e to the, I n pi x over a minus an over 2I times e to the negative I n pi x over a plus bn over 2 times e to the I n pi x over a plus bn over 2 times e to the negative I n pi x over a. Okay, next we can start collecting like terms. So the like term in this case is going to be the exponential, so this is going to give us a summation from n equals 0 to infinity of, an over 2I plus bn over 2 times e to the I n pi x over a, and then added with negative an over 2I plus bn over 2, and then e to the negative I n pi x over a. Is that correct? Yes. Okay, we can make this a little bit nicer, first off, by factoring out some things. So there's nothing necessarily stopping us from adding on a factor of I over I, because I'm sort of trying to factor out the 2I in the denominator. So I'm going to write out I over I for both of these bn terms. What this is going to give us is a summation from n equals 0 to infinity of 1 over 2I multiplied by an plus I bn times e to the I n pi x over a, and then plus negative an plus I bn times e to the negative I n pi x over a. Now, the problem here is the actual expression we're trying to get to is something like this. So the actual expression we want is something like f of x equals a summation and from negative infinity to positive infinity of cn times e to the I n pi x over a. So we have two big problems. First off, our index does not match. Our index starts from n equals 0 to infinity. The one we want starts at negative infinity and goes to infinity. Second problem, we have this e to the negative I n pi x over a term that we can't really seem to get rid of. So the way that we resolve this is that we sort of recognize that this is two different summations. So if we split the summation apart, f of x is actually equal to summation from n equals 0 to infinity of 1 over 2I times an plus I bn times e to the I n pi x over a. And then we're adding a second summation, n equals 0 to infinity of negative an plus I bn e to the negative I n pi x over a. So if we look at the second summation, really what we can do is we can sort of change the signs on n, and that'll give us sort of a summation from negative infinity to 0. And what I mean by that is that this term can be redefined as a summation from n equals negative infinity to 0 of negative a of negative n plus ib of negative n multiplied by e to the I n pi x over a, where sort of we change all the n's to negative n's, and this summation is basically the same thing as the top one, but just in reverse order. So we start at n equals negative infinity, which is going to give us the n equals infinity sort of term up here, and from there, sort of what we can do is what we have to do is basically we have to express out the a n and b n terms, where we have to find what they actually are, because we don't necessarily know what sort of these a n and b n terms actually do under a change in sign of n. So we have to find them using Fourier's trick from the Fourier series, and then after that we have to sort of find out, okay, if we switch the sign on these indexes, how will they sort of be affected? Okay, so we have this Fourier series. Our goal is to find a n and b n. The way we do it is using Fourier's trick, which is something we defined way back in the earlier chapters. What we can do is we can recognize that sine of n pi x over a and cosine of n pi x over a correspondingly represent sort of complete and orthonormal functions, or not necessarily normal, but orthogonal. So what we can do is we can, if we want to find a, for example, so to find a n, what we do is we attach a factor sine m pi x over a. So f of x times sine of, whoops, this is a little bit there we go, sine of m pi x over a is going to equal a summation from n equals 0 to infinity of, let's see, a n sine n pi x over a times sine m pi x over a plus bn cosine of n pi x over a sine of m pi x over a. And then what we can do is we can take an integral from negative to infinity to positive infinity of both sides. So an integral from negative infinity to positive infinity of f of x times sine of m pi x over a is going to equal our summation n equals 0 to infinity, and then we have our integral from negative infinity to positive infinity of everything sort of over here. We just close this with a dx. Now immediately, sort of one of the first things that was defined at the start of this problem was that f of x is only valid from negative a to a. So what that means is that our integral actually isn't from negative infinity to infinity. It's actually from negative a to a, because everything else sort of outside of that just sort of falls away. The same thing is then true for this region, because once again, our region of sort of well-definedness of sort of this Fourier series is only also defined in the region from negative a to a, because f, which is what this series makes, is only valid from negative a to a. If f was defined outside of negative a to a, like even if it was like just 0, then this wouldn't necessarily be true. But because we only have a function in that region, our Fourier series is also only going to be defined from negative a to positive a. So if we do this, we can now take advantage of orthogonality. First off, this part of the integral, this is automatically equal to 0, because cosine is an even function and sine is an odd function. So if we take a symmetric integral, this is going to be a symmetric integral of sort of an odd function, and that automatically just becomes 0. This term right here is equal to a times Dirac delta of mn, where if m equals n, then it just equals a. If m doesn't equal n, it just equals 0. So if we fully write this out, then the integral from negative a to a of f of x times sine of m pi x over a dx, I forgot to add the dx at the top, forgive me, and this is going to equal, and once again, this is a sum from n equals 0 to infinity, but because of this Dirac delta from n, there's only one term that's not in 0 in the sum, and it's the term that equals where m equals n. So we can just sort of replace m with n, because m now equals n. And then we have a summation, which disappears because there's only one term, and this is going to be an times a. We isolate an, and what this gives us is that an is equal to 1 over a times the integral from negative a to a of f of x times sine of n pi x over a times dx. And remember, our original goal is to see how an changes under a change of the index. So if an equals this, what does a negative n equal? Well, the only n dependence is in this sine term, and sine is an odd function. So changing the sign on n, so sine of x versus sine of negative x. Sine of negative x is basically equivalent to negative sine of x. So this is going to give us negative 1 over a times the integral negative a to a of f of x sine of n pi x over a dx. So in other words, this is equal to negative an. So changing the index on n in sine will cause it to sort of switch to a negative. Similarly, we do the exact same situation with sort of the cosine terms. So if we do that, then we, instead of multiplying by sine of n pi x over a, we multiply by cosine of n pi x over a, and we do the same process. That's sort of exactly the same process as up here, so I'm just going to skip doing this. Bn is going to end up equaling 1 over a times the integral from negative a to a of f of x, this time cosine of n pi x over a dx. And in this case, cosine of n pi x over a is even, so cosine of negative x is equal to cosine of x. So b of negative n is exactly equal to b of n. Now, we sort of move back up here. So hang on, let me just copy paste this. I did not write this perfectly. Just take care of, erase a few things. Okay, so we have these two summations. So realistically, we can write f of x equals a summation from n equals 0 to infinity of 1 over 2i times an plus ibn times e to the I n pi x over a plus a summation from negative infinity, which is 0, of negative a to the negative n plus ib negative n times e to the I n pi x over a. We know how an and bn function now when they go under a reverse index. So a of negative n is just negative an. So we remove the negative at the front because that cancels out. And we have an, and then b of negative n is effectively identical to bn. So we just switch this to bn without any changes. And if you look at this now, and also, apologies, I forgot to distribute the 1 over 2i at the start. That also exists. So now, if we look at this, these are basically the exact same summation terms. This runs all of the negative numbers, and this runs all the positive numbers. There's nothing stopping us from combining these summations into a single one from negative infinity to positive infinity of 1 over 2i times an plus ibn times e to the I n pi x over a. And thus we say, okay, Cn is equal to 1 over 2i times an plus ibn. And with that, we're done with part 1. Okay, in part B, we want to show that Cn is equal to the following function. We have the formula for Cn from part A. We also have An, or the formula for An, which we found via Fourier's trick from part A, and also same thing with Bn. This is just a matter of plugging these factors in. So Cn is going to equal 1 over 2i multiplied by 1 over a times the integral from negative a to a of f of x times sine of n pi x over a dx, and then plus ibn, so I over a times the integral from negative a to a of f of x cosine n pi x over a dx. Immediately we can do some we can sort of do distributive property and combine these integrals because they have like terms. We move the 1 over a out first, so we have 1 over 2ia times our integral from negative a to a now of f of x sine n pi x over a plus I times f of x cosine n pi x over a. Immediately here, we can instantly do more distributive property, 1 over 2ia, and then we combine the f of x terms from integral from negative a to a, f of x times sine n pi x over a plus I cosine n pi x over a. And from this point, remember that I just realized I forgot to close out my integrals. Very sorry. Do that real quick. Okay, so we're trying to convert this into a complex exponential. So immediately you should think of Euler's formula. If we do that, then we have 1 over 2ia times this integral from negative a to a of f of x. And then we start turning these into complex exponentials. Sine is going to give us e to the I n pi x over a. Plus, or not plus, minus for sine, e to the negative I n pi x over a, and then we divide this all by 2i, and we add I times e to the I n pi x over a, this time plus e to the negative I n pi x over a, all divided by 2, and we do a dx term to close this off. And from here, immediately, we sort of see that there's a 2i in the denominator and a 2 here. So that sort of suggests that maybe we should multiply I over I on the final term, so right here, in order to get its denominator to be the same, so we can just factor out that denominator. So if we multiply sort of everything here by an extra factor of I over I, what's that going to give us? Well, immediately we can take out the 2i in the denominator, so that's going to give us negative 1 over 4a, because 2 by 2 makes 4, and the 2 i's make a negative. We have left as an integral from negative a to a, f of x, and then multiplied by e to the I n pi x over a, minus e to the negative I n pi x over a. And then we have the 2 i's here making a negative, so a negative one is applied to both of these terms. So minus e to the I n pi x over a, minus e to the negative I n pi x over a, and then everything gets closed out with a dx. So what do we have? We have these two positive e to the I n pi x over a terms, so this term cancels out with this term automatically. These two make negative 2. What we have left is 1 over 2a, because I'm factoring the 2 out and also the negative out, times the integral from negative a to a of f of x times e to the negative I n pi x over a dx. And if we look up above, this is exactly what we wanted to get from this problem. In part C, we're asked to sort of take the two results we got in part A and part B, which are these two formulas, and we're asked to replace the variables in terms of sort of f of k, delta k, and k. So let's start with the first one that we got from part A, which is that the f of x function is equal to this exponential linear combination. So first off, k equals n pi over a. So we have n pi over a, so we can instantly change this to a summation from n equals negative infinity to positive infinity of cn times e to the ikx. Next, we have the cn that we want to replace. So what we have is that f of k is equal to square root of 2 over pi multiplied by a times cn. What we can instantly do is we can just reverse everything to define this in terms of cn. Cn is going to equal 1 over a times square root of pi over 2 times f of k. So we replace that here. This is going to give us a summation from n equals negative infinity to positive infinity of 1 over a times square root of pi over 2 times f of k multiplied by e to the ikx. This is going to give us, if we just move everything out of our integral, this is, or not our integral, of our summation, then we have 1 over a square root of pi over 2 times the summation from n equals negative infinity to positive infinity of f of k times e to the ikx. Now, this isn't necessarily exactly what we have equal to this, but we note that there's an extra delta k factor here. So what they say is that delta k is the increment in k from one end to the next. So if k is equal to n pi over a, then what that means is that if we go from n equals like 1 to n equals 2, then k is going to change by pi over a. So delta k is going to equal pi over a. So that delta k is another way of saying dk by dn, basically. So there's a delta k term here, so that sort of suggests that maybe we should multiply by delta k over delta k and see if that bottom delta k sort of cancels out with this to make the 1 over square root of 2 pi. So let's do that. Delta k over delta k, and the bottom one I'm going to hope cancels, so I'm going to write this as actually pi over a. So that's going to, what's that going to give us? It's going to give us 1 over a square root of pi over 2 multiplied by, and then it's at the bottom, so to bring it to the top, we switch the denominator and numerator, multiplied by a over pi times the summation from n equals negative infinity to positive infinity of f of k times e to the I k x delta k. And then from there, we have the a's cancel, the square root of pi at the top and the pi at the bottom cancel out to just square root of pi at the bottom. So this is going to equal 1 over square root of 2 pi times a summation n equals negative infinity to positive infinity of f of k times e to the I k x delta k. And with that, we have finished the first part of this. We have f of x. Next thing we want to do is this cn term. So immediately we can start by replacing the cn. So this is going to give us 1 over a square root of pi over 2 times f of k multiply it, no, and then this is going to equal 1 over 2a times the integral from negative a to a of f of x times e to the negative I and pi x over a. And you know what, in fact, I can just do the exact same thing I did at the start and change this to k, so this is going to be negative ikx. Now we have some like terms we can cancel out the a's, so what we have is f of k is going to equal square root of 2 over pi times 1 over 2. The square root of 2 at the top and the 2 at the bottom is going to cancel out to just square root of 2 at the bottom. So this can be just rewritten as square root as 1 over square root of 2 pi. Multiplied by our integral of f of x times e to the negative ikx dx. And if we look, this is exactly equal to what the book says we should get. And with that, we have finished part 3. Okay, final part. We have our f of x and f of k functions that look very similar to sort of the Fourier transforms, and we want to take the final limit that a goes to infinity in order to sort of turn these into Plancherel's theorem. So if we look at this, these are already very similar. This one converts very easily because the only difference here is that the integrals are going from negative infinity to positive infinity over here. So we literally, in the limit that a goes to infinity, we just replace these integral limits from negative a to a to negative infinity to infinity, and we have sort of this part. So this part, we don't have to worry about. It's already taken care of. The proof is pretty much trivial. For this one, what we have to do is we have to recognize what delta k actually equals. So if we rewrite this, f of x is equal to 1 over square root of 2 pi times a summation. First off, this is an index in n, and this is an integral in k. So we want to convert this from indexing in n to indexing in k. But we know that sort of k takes on the following form. K equals n pi over a. So if n is going to infinity, well, pi and a are sort of both, you know, constants. So if n goes to infinity, or if n goes to negative infinity, k also sort of has to follow suit. So k equals negative infinity to infinity is a valid sort of substitution for this. Note that technically if a actually equals infinity, then k goes to like pi and negative pi respectively, but a isn't infinity right now. A is still just an arbitrary constant that's equal to the width of whatever our function well is. I haven't done the limit yet, so this is a valid substitution. Then we have f of k times e to the ikx times delta k. Now, what happens here if a goes to infinity? Because delta k is equal to pi over a. So if a goes to infinity, then delta k is going to approach sort of an infinitesimal element, because this is just going to get larger and then the pi stays the same, so this gets smaller and smaller. Delta k can be rewritten just as dk, effectively. So if we rewrite this, then the limit as a goes to infinity of f of x is going to equal something like 1 over square root of 2 pi times our summation k equals negative infinity to positive infinity of f of k e to the ikx dk. And this is pretty much the definition of converting like a summation into an integral, because this super small dk is going to mean that each one of these sums is going to contribute negligibly to the final summation, and that's pretty much the definition of an integral. So this can just literally get converted by definition into an integral from negative infinity to positive infinity of f of x times e to the I k x dk. And with that, we are done with this problem.